Hi, everyone. So today I will talk about quantum number theory and cosmic Milli charge background. Uh, so let's get into it. So quantum number theory, really, it's just number theory for quantum numbers. And of course, there has been a lot of different studies, but I think it would be very exciting to group all these studies together. And that's why I coined this term to kind of describe all the number theory application on quantum numbers and vice versa. This kind of research can indeed inspire research in the pure mathematical studies, as we will demonstrate. So, but first, let's get to the physics motivation of this specific talk. So there are many interesting applications, but one of these um, kind of, you can say, a little bit of a hot topic is Milli charge particle. There has been a lot of recent study about the Milli charge particle. And also, of course, historically, it was also a very popular study. So there's long-standing question of is electric charge quantized to what unit and why? And there's also strong connection of this problem to monopoles. In fact, fractionally electric charge particle, or in the kind of higher energy theory, would be a particle with a small hypercharge. This is actually a generic prediction of string theory. It's also a product of grand unification theory, and it's a simple example leading to our consideration of quantum number theory. Finding Milli charge particles can also be a strong probe for early universe reheating cosmology. That would be the second part of the talk. And because of all these recent interest, I'm writing a review about the Milli charge and fractionally charged particle. Furthermore, we can have, well, following the discussion, we can have the pure Milli charge particle and the effective kinetic mixing Milli charge particle. Today, we will focus on the right, this case, meaning that you can have effective Milli charge particle produced when your standard model hypercharge is going through some kinetic mixing with U1, some new hidden U1 symmetry. We will call it U1H from now on because it's hidden. And in the end, in the kind of low energy effective theory, you will get this psi particle will become Milli charged under the hypercharge, the usual U1 hypercharge. And then, of course, after the electroweak spontaneous symmetry breaking, this psi particle will then become the Milli charge particle with a small electric charge. And kind of the new structure that we introduce to connect to number theory would be that we consider chiral symmetry. So chiral symmetry will lead to potential gauge anomaly because if you impose such a symmetry or you have a theory that has this fundamental gauge symmetry, if the quantum correction can break that, it will induce anomaly. So now you need anomaly cancellation to make sure your theory is healthy. And this surprisingly is corresponding to the number theory PTE problem, which I will explain further. And eventually we are able to provide a sharp predictions for the Milli charge particle spectrum. Okay, so let's get into the detail. With the Milli charge particle that already has a hidden U1H, we'll add an additional chiral symmetry U1X to the psi particle. Now here, for simplicity and for to write things more explicit, we split the Dirac spinner, usually this psi particle will eventually become the mealy charge particle. We rewrite it as 2 Weyl spinor and plus its Hermitian conjugate. And then we assign this psi1, psi2 particle with +1 and -1. Of course, this is the common way to write a Dirac spinor into a Weyl spinor. And furthermore, we have the psi1 and psi2 with different charge. So now this A and minus B are the charge. So these are now actually quantized number because they are kind of this based on this the actual charge of this U1 gauge group. So these A and B are numbers. If A is not equals to B, then this mass term is forbidden. So you don't have this mass term in the higher energy. So now all of the mini charge particle mass will be generated through kind of this type of coupling, this Yukawa coupling with the dark Higgs, with the additional Higgs. So just like standard model, we can now have this new Higgs to generate the mass naturally. Yes, this is the way we write it. And again, we assign 0 charge for these dark Higgs, but charge of 1 through this chiral gauge symmetry. Okay, so this will allow a Yukawa coupling of this form. And after the spontaneous symmetry breaking, it will give us a small mass. So this M12 will be the kind of mass of this Dirac fermion. And because you have MC as the UV cutoff scale, suppressed by a small number, which is the VEV of this dark Higgs divided by MC. So this mass is naturally light. Let's say if you have a Gus theory, but your VEV is all the way down to GeV scale or TeV scale, then now you naturally can have a mealy charge particle that is much lighter than your cutoff scale. Okay. So far, it's pretty straightforward. And even the next step is also quite straightforward. Now, you actually have to start to add more field content because you know this theory might be sick. As we'll tell you, this theory is actually not self-consistent because there will be gauge anomaly. So first, you actually want to introduce more Weyl fermion in order for you to have a chance that this theory is healthy. And that's actually already a very interesting point, but we'll demonstrate even more later. So basically, with this structure, again, the spontaneous symmetry breaking will give you the n by n mass matrix, which are suppressed based on this number. Now, what's the most interesting thing would be what are these actual numbers? Because not all the number will satisfy the following condition that will be the key to this talk, which is the anomaly condition. So the anomaly condition requires that, for example, if you consider the triangle diagram, that involves this U1x, graviton, and graviton, this give you this anomaly. But you have to cancel the anomaly, so then you need your charge to sum up to be the sum of AI will be equal to sum of BI up to n. So I runs from 1 to n. N is currently not specified. Secondly, you also need the square sum of these numbers to equal. And thirdly, you need your power to the third sum of this number to be equal as well. And interestingly, this problem itself is called the Precious-Terry-Ascol problem, which I'm still learning how to pronounce properly. But anyway, so this is a very important thing. And there are some studies, but none of them are actually explicitly connecting to the number theory, except the paper by David Tong, they actually did connect to the Fermat's last theorem. I shouldn't say they didn't connect explicitly. I would say maybe they didn't go into the depth of this math problem, which we actually did, as we will show you. And also their setup is different. So they are not corresponding to the PTE problem. They may correspond to other number theoretical problem. Okay, but then what you find out is that you are satisfying this degree 3 PTE problem. So degree 3 because this is only to the third power sum. But if you have fourth power, there will be degree 4. Fifth power, there will be degree 5. Another thing is that you can, of course, have huge amount of solution. But if you limit your interest to n is equal to k plus 1, in our case, k is equal to 3, then n will be equals to 4. Then this would be the minimal solution. It will be the ideal solution. So we'll focus on this ideal solution. So in fact, this points to the n equals to 4. And in fact, when the n is equal to 4, it corresponding to exactly 4 millicharge particle. Because now you have a total of 4 Dirac spinner split into 8 Weyl spinners. Awesome. Yes. Okay. And furthermore, now we can look at the symmetric solutions. So now we understand there are these PTE problem with ideal solution. So n is equal to 4, k is equal to 3. This is a well-known, well-studied problem in number theory. Now you study something more. So we started to study something that people didn't study a lot in number theory that is called symmetric solution. Because we found out that this symmetric solution actually have mathematical meaning. Symmetric solution meaning that if you add a minus sign, if you flip a sign, this set of solution is the same. For example, this will be one of the examples that is the solution, and it's both ideal and symmetric. Ideal because it's 4 of them. Symmetric because if you add a minus sign, it's symmetric. It's the same. And we actually prove a new theorem in our math paper that we also put out actually 2 weeks ago, that we found out that these symmetric solutions actually grow with h, which is the maximum number of the maximum value of this solution. So this is already a non-trivial result that we have to prove in a 30-something page math paper. And we want to actually further prove another more involved conjecture, but we're still working on it. Awesome. And interestingly, so the reason why we study this ideal symmetric solution is because if you satisfy both the ideal and symmetric solution for this PTE problem, you find out your spectrum actually split into 2 sets. So you have 4 millicharge particle, but 2 and 2, you have nearby degenerate mass. Meaning that if you find 1 millicharge particle, let's say in GeV, the other one might be in 1.5 GeV. So you should find 2, and actually you can find up to 4 for this kind of ideal minimal solution. So 1 is not enough, you need 4. And once you find 1, you probably can find another one nearby. So the degeneracy of the higher order, meaning that the splits of between these comparing to the larger splits is actually very suppressed. And this type of situation will definitely impact experiments and cosmological searches. So in our first paper, we only focus more on the theoretical aspect, but there is a lot of experimental and cosmological impact that this paper will have. Okay, so here's a summary. Based on our construction, there is chiral symmetry will provide naturally light midi-charged particle. Anomaly cancellation conditions give us a degree 3 PDE problem. Sharp prediction of minimum of 4 midi-charged particle state, which is the ideal solution. And symmetric solution will actually dominate. This is actually our conjecture. We prove that it's abundant, but we're actually trying to prove that it's actually dominant and leading to the doublet LTT spectra. And we also show a new number theory result that the symmetric solution is actually dominant among the PTE solution, the ideal PTE solution. Good. So this is the first part of the talk. The second part will be more on the cosmological and search, cosmological studies and search, and it will also be very brief. Because basically, I just want to tell you the program of probing reheating cosmology with experimental searches for midi-charged particle. So we know that reheating is a phase that after inflation, you want to produce standard model particle because the universe is flat and empty. There's nothing there. So you have the reheating for your inflaton to decay into standard model particle to give you what we have now. But the problem is we don't know what the reheating temperature is. It can go from all the way from very high temperature to a very low temperature. We really don't know the reheating temperature almost at all. So I want to ask the question, can we use experimental search to learn about the reheating temperature? And this is the results of our paper, the previous paper, that this constraint of midi-charged particle actually will depend on the reheating temperature. Meaning that if my reheating temperature is only 5 MeV, this region will be constrained for a pure midi-charged particle. Y-axis is the charge comparing to electric charge. So this is 1. This is all the way down 10 to the minus 12. And then the mass of a midi-charged particle in terms of GeV is of this range. Of course, you can naturally extend to high reheating temperature, but we focus here because there are many experimental searches, including some of the ones that I proposed, including Formosa, Fermini, SubMed, which I didn't propose, but it's a Korean lead experiment, and Millikan, which is basically the father of all of these small-scale experiment for midi-charged particle, or mother. Yes. So anyway, if you can find, the point is, if you can find a midi-charged particle, for example, here, then you will constrain your reheating temperature to below 100 MeV. So you can say, what if I don't have the pure midi-charged particle? What if it's kinetic mixing midi-charged particle? The similar story follows. There will be cosmological constraint based on reheating temperature. And if you find a midi-charged particle, you can constrain your reheat temperature. And this kind of study can extend to, again, higher temperature and many other beyond standard model particle. So both the discussion in the first section and second section are actually more generic than midi-charged particle itself. But midi-charged particle is a very clean and nice example to demonstrate the point. So finally, I want to mention, as I already said, there are several of these midi-charged experiments that I'm helping. Some of these are proposed by myself. Actually, I think all these three I propose all these three. And we are actually already have prototype and already taking data. So the first two already are taking data from prototype. The last one, I think we're waiting for the chance to install it and can also take prototype data from the prototype. And here is just a quick summary of how these probes are. This is, again, the axis is the mass of a midi-charged particle. Y-axis is the fraction of the charge. And you can see these color one are the probe, and it will correspond to different reheat temperature that you can probe. And here is just some figure and the students that are involved. There were more, but I list some of the key contributor to installation, and actually some of them graduated. So yes, and now actually he's in maybe he's in the audience. Okay, he moved to the UK just like I did. So summary. Um, so this talk, we try to bridge new results in quantum field theory in terms of anomaly cancellation, mathematics in terms of number theory, all the way to phenomenology, both in cosmology and experiments for this mini-charge spectral prediction. And we can probe mini-charge particle to reveal cosmology, the reheating cosmology. And there are many dedicated small-scale experiments that are being built to study mini-charge particle. And as I say, this presentation is very preliminary. There will be a lot of improvement, both on the slides and adding more references. So if you think there are things that should be mentioned and it's not mentioned, please email me and let me know. Thank you. Thank you very much.